Welcome to my keynote, Physically Large Antenna Arrays When the Near Field Becomes Far-Reaching. I'm Emil Björnson. I'm a professor at the KTH Royal Institute of Technology and at Linköping University in Sweden. And in this talk, I will tell you about what happens when we have really physically large antenna arrays and use them for wireless communications. And as you can notice from the title of the talk, I will talk about near field behaviors and various things that are happening when the arrays are large. So to start with, why are we using antenna arrays in wireless? Well, there are basically two important things we can do when we are deploying an antenna array at the base station. We can transmit directive signals with a controllable directivity towards users where they are, so the signal energy is actually arriving to a large extent where we want it to be. And that's what we call adaptive beamforming. We can also make use of spatial multiplexing, and this really means two different things. One is that we can serve multiple use at the same time and at the same frequency, and also that we can send multiple streams to the same user if we have sufficiently different propagation paths. And this is illustrated here by 3 different beams pointing towards one user here and 2 beams pointing towards the same user here. So here we are spatial and multiplexing 3 different signals. And this whole thing is often known as MIMO, or multiple input, multiple output as well. Just to get a sense of how do we do adaptive beamforming? Well, if we have 2 antennas that are transmitting the same signal at the same time, they will propagate like this. And when we are measuring the superposition of these 2 radiated signals at any location in space, we will either get constructive or destructive interference from these 2 different transmissions. In particular, you can see that there are certain directions here upwards where the wavefronts from the 2 antennas seems to be aligned. And this is the direction where we will see constructive interference, while another direction we will not. So another way of viewing that is that we have 2 antennas, each one is individually radiating the signal with no particular directivity from the beginning. But still, when we are transmitting from 2 antennas at the same time, the same signal, each of them having this radiation pattern, then if we start to measure the strength of the signal that we get in different directions, it will look like we have these kind of directive transmissions upwards here. If you would like to adapt the direction of the signal, what do we do? Without moving the 2 antennas, we can actually just change when we are transmitting from the 2 antennas. The right antenna here is delayed. Therefore, the green wavefront here have not moved as far as the green one from the first antenna, the left one. We can therefore see that the wavefront seems to be adding up in this direction upwards to the right. This is where we will see constructive interference. So if we start to measure the strength of the signal in different directions, we will see that we actually have like a single beam upwards here, and in that direction there's very little. And then there could also appear some kind of side lobes or side beams in that directions. And nowadays in 5G we are talking a lot about massive MIMO. MIMO with something that's being massive. What does really massive mean? Well, if you look at the Merriam-Webster dictionary, massive means bulky, weighty, heavy, large, solid or heavy, or large in scope or degree. Which of these definitions is it that actually applies when we are saying massive MIMO? Well, this is how one of the latest Ericsson massive MIMO arrays look like. Inside this box, there are 32 radio chains connected to 128 radiating elements. There's essentially 32 antennas. It weighs 12 kilos. It transmits 200 watt over 200 megahertz of spectrum in the 3 gigahertz band. And there's integrated circuits for do all the signal processing that we usually are considering in the massive MIMO area. Even if this is something that we call massive MIMO, it is not because it's bulky or weighty, it's because it's large in scope, in the sense that we are considering more antennas here than we were doing in the past, when we maybe only had 2, 4, or 8 antennas. Now we have 32 or maybe 64. But the point I want to make here is that these things are not large, what we call massive MIMO, on which the marketing here is calling massive MIMO. So in the 3.5 or 3 gigahertz band, a 5G array with 32 or 64 antennas, it might be half a meter times, almost a meter. We put it on the rooftop, and if you're close to it, it is large. If you're far away, it is not large. So if we zoom out here, This massive MIMO arrays might contain many antennas compared to what we had in the past, but they will look small, and therefore they will be in the so-called far field of the user. And when we're transmitting towards the user, it will be like sending this kind of signal beam towards it. But what if we would in the future deploy antenna arrays over much larger surfaces, like over the entire facade of the building here? This will be an extremely large aperture, tenth of meters large in the diagonal. And in this case, what I have been alluding to here is that the transmission might not look like a beam like this, even in a line of sight scenario, but it might be more like a focused ball of energy around your receiver, and then other locations you will not see any strong amplification. So with this, we are not in the far field of antenna arrays anymore when these beams are appearing, but in what we can call the radiative near field. And in this keynote, I will go into detail to explain what is actually happening in these situations, and also what would be the actual benefits of this evolution if we would build really physically large antenna arrays. And as a starting point, let me talk about the near field of a passive antenna. One antenna that always have the same radiation pattern. It might be at the size of the wavelength. So the electromagnetic definition of the near and far field is like this. You have a transmit aperture here of length capital D. I divide into two parts, D over 2 and D over 2. I have a measurement point here where I would like to figure out how the electrical field looks like. And I use the lowercase d to denote the distance to this measurement point. And then geometrically, there will be a larger distance here to the endpoints, the outer corners of this antenna aperture. D plus delta, and we can compute delta using some trigonometry. And if you would like to compute the electrical field at a location here, what you should do is to take an integral over the aperture and figure out what will be the contribution of the radiated signal from different parts of it. And one way of computing this is to get a formula like this. You will get the energy that is falling off with the distance set here, or 1 over that. And there will be a phase shift because these are sinusoids with a certain wavelength lambda. So we have e to the power minus j 2 pi divided by lambda times z. This is how much it has been phase shifted on the way to the receiving point here. And usually it is just to integrate over this in order to get the field strength here. But if we are close by, it is not only the radiated fields that are appearing, but also some other behaviors, reactive behaviors like evanescent waves and magnetic coupling and these type of things that are around a transmitter, but it's not really radiating away from it. Here, instead of just multiplying this term here with a 1, there are some additional terms that one can model. When you're very close, they make a difference, but not when you are at typical distances. One can show that there is something called a Fresnel distance, which is computed based on the total length of the aperture, D, and on the wavelength, and there are some factors here. There are different ways of approximating it, but the point is that this is not a large distance. What we will be focusing on in this keynote is what I call the radiative near field. This is when we can neglect these two terms, but still this integral will not be an integral over a constant, but there are variations of this integral within the size of this aperture. So what does that mean? Well, it means that we cannot neglect the distance difference between the lowercase d here and the lowercase d plus delta. As a starting point then, let's figure out when we can neglect it. So let's figure out how large is delta. Well, we take the total length d here, we take this capital D over 2, we square both of them, we add them up, and we take the square root, and in this case we'll get the total length here. Then we subtract d, and if you make a Taylor approximation, you can show that this is approximately capital D squared divided by 8d. Okay, so this is the difference here, distance. And then in the electromagnetic literature, what we often say is that if this is carrying over, to have a phase difference between the direct signal here from the center and from the edge that is smaller than pi rate, which is a sort of arbitrarily selected number, then we can neglect the effect on this phase shifts here. And if we now equate this pi over 8 should be greater than this distance multiplied with 2 pi over lambda, which is determining how much the phase will be shifted over that additional distance. And we say this should be smaller than pi over 8. Then we can rearrange and figure out that when the distance to the measurement point here is greater than 2 times d squared, the capital D squared, divided by lambda, then we can neglect it. And this is known as the Fraunhofer distance. Well, this was the Fresnel distance. From a transmitter, we first reach the Fresnel distance. At that point, we can neglect the reactive fields. And then we have what we call a Fresnel region. And in that point, we need to take these radiative effects into account. And then when we reach the Fraunhofer distance, we can neglect all of the phase shifts. And we can treat this as just being a electrically small antenna, which is having a constant behavior here. It's like a point source. And what I will be focusing on is what is going on in this Fresnel region, particularly when the transmitter is large. Since we are considering here an antenna at the transmitter and the measurement point, then even if there is no concept of a receiver when we are talking about it electromagnetically, we can turn this around and say that this is a point source, a small transmitter, and this is an antenna aperture that you're receiving. And this will tell you more about what is actually happening here. So say that we have a transmitter sending out the signal. It is a spherical wave here that's propagating, and then the wavefront is hitting a receive antenna here at distance lowercase d. Over this aperture, this curvature of the wave might or might not be visible. And if we once again say that, well, if the phase shift between the center and the edge is smaller than pi over 8, well, in that case, we can neglect the variations here, and we can say that, well, then this spherical wavefront is approximately constant over this aperture, the receiver. And doing the same math again, we get the same formula. This is the Fraunhofer distance. So when we are at distances larger than the Fraunhofer distance, the wave that is spherical will look like locally plane, and we can neglect all of the curvature effects. One can also talk about the amplitudes being different because there are different distances to the center and the edge here. Usually those effects are also rather small. And when I say small here, say that we are a 3 GHz band. We have an antenna that is having a total length here of lambda, the wavelength, which is 0.1 meter. Then we can neglect the amplitudes if we are at 0.12 meters. We can neglect, based on the Fraunhofer distance, the phase difference. If we are at 2 capital D squared divided by lambda, we put in lambda here. We get lambda squared divided by lambda. It's 2 lambda. So when we are at 0.2 meters, we can neglect these phase differences. So for a reasonably sized antenna, we can neglect all of these effects. We will now have a look at physically large arrays, and then the physics are the same, but we might actually be in the radiative near field. And to understand what is actually happening, then consider now that we have a transmitter once again that is sending out a radio wave, and we have an array of a total length W, but it is divided up into small antennas, each of them having a length D. And I will now define what I call the Fraunhofer's array distance, DFA. This is a distance after which the angular field distribution is essentially independent of the distance. So we will see a plane wave over the entire aperture. And I think a practical operating regime that can happen here is that we are in the far field of the individual antennas. So the distance here is larger than 2 capital D squared divided by lambda if you're considering each of these individual antennas. So we have a locally plane wave over a receiver antenna. But if we are considering the different antennas here, and we are taking the same computation, but we are replacing capital D with capital W, then the distance might be in the near field of this receiver antenna array in this sense, that the distance is smaller than 2 capital W squared divided by lambda. And in this case, we will see a locally plane wave over each antenna element, but we can notice the curvature when we are comparing the received signal at the different antennas. So as an example, when this could happen, Then say, once again, we are at the 3 GHz frequency where the wavelength is 0.1 meter. I assume now that the total length of the array is 10 lambda, so 1 meter. Then this Fraunhofer array distance, we compute it like this. It will be 20 meters. If we are increasing the length of the array up to 10 meters, then we should put 10 into this W here. We increase W by a factor 10, we square that, we increase the entire thing by a factor 100, and now we go from 20 meters to 2 kilometers. So with a physically large antenna array, we might come to a situation where almost everyone who is served by the array will be closer than in Fraunhofer array distance. But we should then remember that, is this actually the right metric? We were just arbitrarily saying that, well, when the phase shifts over the array is smaller than pi over 8, then we should neglect the effects. Is this the right metric? That is what we will consider next. So we need to go in and model effects that we will have in the radiative near field in more detail. And suppose we have a user at a distance set from an antenna array that is divided into different small elements, and it's L by L in size. So this is a square. Then if we are in the far field, how do we compute the path loss or channel gain? Well, we would be taking the total area of the aperture, L times L, so that's L squared. Then we should compare that with the surface area of the sphere which has radius set, because this is how large the sphere of signal energy will be when it's reaching this receiver. And that surface area is 4 pi z squared. So the ratio between these two things will be the far field path loss. But this is assuming now that we have a plane wave coming in over the surface, and maybe that's not the case. In the near field, we need to consider certain things. One thing is that the different antennas in this array will have distances that are different. The amplitude might be different. Moreover, when you are close to the antenna array, you will see the different antennas from rather different angles. And then the antennas will look like they have a different size. Even if they have a physical size that are the same, their effective areas of them will be different. Those that are further away will capture less energy because you see them from a different angle. Finally, the signal that is coming in to the antenna array will come in from a particular angle. That is determining what polarization losses we will have, and those will also vary because the signal have a particular polarization direction when we are reaching the array, and the antenna elements will also have a particular preferred antenna polarization. So those variations will also be there. And if we are taking these different properties into account, and we compute the actual path loss or channel gain from an antenna array like this in a way that is consistent even if you are close by, and we did that in a paper from last year, we are getting a free space channel gain of path loss formula that looks like this. From a distance set from the center and the width length of L. And it looks somewhat complicated, and the important thing is not exactly how this one is behaving here, but rather that it is containing this beta set, the far field path loss, at a few different locations. And we have some ratios and inverse tangent and things like this. We can use it, but what will happen in different cases? Well, in the limit, when set is large, then beta set is small. So here in the denominator, where we have beta set, we can neglect this term compared to 1, this term compared to 1. Here, this will be a small thing. Tangents of inverse will be almost linear. And you will get beta set divided by 3. 3 pi times pi beta set, that is 2 or 3. We add them up, we get beta set. So when we are far away, then we will be able to just use the formula. So there is a consistency here. So this formula always works. But if you take the limit instead, you let the length of it go to infinity in both the horizontal and the vertical dimension here, this will converge to 1 over 3. And then you might wonder, why 1 over 3? Well, the transmitter is sending out signals in all directions, and half of it will reach the receiver aperture here, because it's sort of capturing half of the world. So that would tell you that we should receive half of the power, which is almost true. Apart from that, we also have these polarization losses that we need to take into account when we are very close, because some of the energy will reach the surface, but not with the right polarization. So therefore we are losing 1/3 in addition, and we only get 1/3 in total. So when do we actually need to take all of these effects into account and use these more complicated path loss formulas? Well, here I was just saying that when Z is much larger than L, but how much larger? So here's an example of this. I am 20 meters from a square array, and I'm varying the diagonal in meters of this array. And I'm increasing it here up to 10, and then things starting to be divided up. So when we are at distances that are then closer than 2 times the diagonal, which happens here, we have different behaviors. And what are these different curves that I'm showing here? Well, the upper curve is the far field approximation, the beta Z formula, the one that we're used to using. It is increasing quickly, and it's overestimating what kind of channel gain or path loss we will get. If we are taking only that we have different distances to different antennas, well, then we are getting the blue curve. If we are also taking into account that we have different effective areas, we get the black curve. And if we take in also the polarization losses into account, we get the red curve, which is the most accurate one. So when we are at this distance, we should start to care about that the channel gain will not be the same as in the far field. And this is something I will refer to as the Björnson distance, because I think we were the first noticing it in this work here. And it really happens when we are at a distance that is shorter than 2 times the large dimension. So in this case, the large dimension is 10, and we double that to 20. That is when we start to decouple here. So what does that then mean for things like array gain, channel gain, something like this? Well, suppose we have a transmitter here that's sending out an isotropic antenna. Here I have an array with different elements, and I assume each of them have a diagonal, which is d. Then the total length here will be, if I have n elements, so there's square root of n in each dimension here, well then the total length will be square root of n times d divided by square root of 2, because when the diagonal is d, every side is d divided by square root of 2. And I will now like to figure out something I call the normalized antenna array gain, or just what is the difference between the actual channel gain that we're getting and the far field channel gain that you will be getting if you were sufficiently far away, so you can neglect all these effects that I was considering. There are then some different distances that we have talked about. So let's figure out when this ratio actually becomes something different than 1. One thing was the Fraunhofer array distance that I mentioned. So in this case, we should take the largest dimension. It is n, square root of n times d. So this is the diagonal here. We should take that square root of n times d, we could square it, so we get n d squared. Then we should divide by lambda and multiply with 2. So this will be the Fraunhofer array distance. And if we now remember that 2 times d squared divided by lambda was the Fraunhofer distance, df, then this is just n times df. So we are getting a Fraunhofer array distance that is scaling linearly with the number of elements that we're putting out in these 2 dimensions. The other thing I was saying was that we should take the largest dimension, which is once again d times square root of n, and we should double it, and that is the Björnson distance. So when are things happening here? Here's a simulation example. I have an antenna array which is 100 by 100 antennas, so 100 times 100. And each of them have lambda, the wavelength, as its diagonal. And now I'm showing what this ratio becomes at different propagation distances. And to make this wavelength independent, I would characterize in terms of this Fraunhofer distance. So I have the Fraunhofer distance, 10, 100 Fraunhofer distances, 1,000, and 10,000. And 10,000 is what we're getting if we take 100 times 100, plug it in here, then the Fraunhofer array distance will be equal to that number. And the Björnson distance will in this case just be 100 Fraunhofer distances. So what we can see here is that the ratio is small in the beginning, when we are very close and we try to use the far field approximations, then it goes up. We reach a point here when we have reached the Björnson distance, then the loss here is small. If we are shorter distances, we have a larger distance difference. So here is maybe 0.95, which in a dB scale is essentially nothing. And then it's increasing up to essentially 1. And then we continue for at least 10 times here up to the Fraunhofer ray distance. So I would say that there is no evident impact of the Fraunhofer ray distance on this kind of curves. It doesn't seem to provide us with an important characterization of the near or far field, while the Björnson distance is at least telling us when we will be able to achieve at least 95% of the gain. Nevertheless, when we are in between the Björnson distance and the Fraunhofer ray distance, we might say that we are doing beamforming in the Fresnel region. The Fraunhofer ray distance still have a relevance. When we are further away than this one, then we have this effect that I was talking about earlier. Pi rate will be the largest phase shifts that we can see. And because of that, we can model the incoming wave as a plane wave when we are designing transmitter-receiver algorithms to do beamforming. We can use what we call the array response vectors, which is just determining, from which angle did the signal come, and it was a plane wave from that angle. Yeah, let's design our receiver transmitter based on that. When we are closer, we can get the full gain, the same gain as we will have in the far field, but we will have a spherical curvature. Not over every single element, but between the elements, which means that we need to stop using the array response vector and instead use some kind of beamforming method that is compensating both from the incoming angle and from the distance from where it came. But as long as we are compensating for that, we will be able to achieve the same kind of path loss that we will get if we are in the far field. What is then of interest left to talk about then? Well, there are some interesting effects that happens here. So if I have my transmitter array here, I'm focusing at the point at the distance f. Then the beam will become wider and wider because what I call the angular 3 dB beam width, which is the angular window within which we will, in the center, get the maximum amplification of the beamforming, and then it will lose towards the edges here, and here we have lost 3 dB or half of the power. Then this beam width have the same angular size all the time. But of course, if the angle is the same, then the actual distance in meters will become smaller and smaller the closer we are, and larger the further away we are. But this is nothing that is changing between whether we are in the far field or near field. The angular beam width is the same. What is, however, interesting, and something that we proved in a recent paper here, a primer on near field beamforming for arrays and reconfigurable intelligent surfaces, it's that we are getting also a limited depth of focus, which was known in antenna propagation literature before, but this theorem is a new thing to characterize how large is this depth of focus. Just as the gain is reducing in the angles here to the left and to the right, if we are focused on this point, it will go down when we are closer and it will go down when we are further away. And the interval where we will see an amplification of the beamforming, which is up to 3 dB from the maximum one in the focal point, we can compute the lower point and the upper point. It's the Fraunhofer ray distance and the focal distances that you multiply in the numerators. In the denominators, you have the Fraunhofer ray distance plus 10 times the focal distance. And here we have Fraunhofer ray distance minus 10 of f. Since we compute the difference here, when the focal point is sufficiently far away, we will subtract something here that is larger than the Fraunhofer ray distance. And when that is happening, well, we get a negative number here. And particularly at the point where we get zero division here, then we will have a beam that continues all the way towards infinity. And that is when we need to replace this with infinity. And when does this happen? Well, that is when the focal point is the Fraunhofer ray distance divided by 10. When we are close to that, we get what I call finite depth beamforming. The beam have a limited depth. So here's an example of this. If we have an antenna array, we transmit to a signal in the far field, then it will continue the amplification behind the user all the way until infinity. But there will be a lower limit on when we can see the amplification. And before that, there is almost no signal gain. However, when we are focusing in the radiative near field, there will be a lower limit and an upper limit. Beyond that one, we will not see any amplification due to beamforming. Then the starting point here is the Fraunhofer ray distance divided by 10 when we are transmitting far field. And what is then the impact of the wavelength or something like this? Well, if we are considering antenna arrays with a fixed size in meters, then when we are going up in frequency, so that the wavelength is going down, then the Fraunhofer ray distance is proportional to lambda to the power minus 1. So higher frequency means that this distance becomes larger and we will see more near field beamforming effects. However, if the number of elements are fixed in our arrays, then we get the opposite effect. So the same number of elements and they have the same gain as before, then the Fraunhofer ray distance is instead shrinking with wavelength. So here's another illustration of this. We have a square array with 100 by 100 antennas, and each of them have the wavelength as its diagonal. And I'm showing the amplification that I will get at different distances, multiply with the Fraunhofer ray distance. This is the same scenario as I was showing before, but then I was only showing this maximum gain curve here. And now I have also increased the range up to 10 to the power of 5 times the Fraunhofer distance. And I'm focusing beams at different locations. I'm focusing in the red curve here at infinity, so infinity far away. Then we get an amplification, that is the maximum one. And at the Fraunhofer ray distance, I also get that one, and then it starts to fall off. And at the Fraunhofer ray distance divided by 10, I only get half of the array gain. So for that reason, I am losing 3 dB. And then it goes down, and when we're very close, we don't see this beam at all. If I'm focusing at the Fraunhofer ray distance divided by 10, then the amplification that the beam is providing me with will having its maximum value at that point, and it's what you get in the same thing as you can achieve in the far field. And then it goes down when you get closer, and when you get further away, you lose an array gain, and it goes down towards infinity to 0.5. And if you are very close, for example, you are focusing here at the Björnson distance, we are seeing a small loss here in array gain compared to what we will have in the far field. But in particular, we have this finite depth. So it starts slightly before and ends slightly after, and you almost see nothing in the far field at all. So what's the point here? Well, the Fraunhofer ray distance, nothing special really happening around there. The Finite-Depth beamforming happens when we are closer than the Fraunhofer ray distance divided by 10. Then that is when we start to see that at infinity we don't get much beamforming gain. And at the Björnson distance, the array gain starts to taper off as well. So what does this mean in terms of physical distances? Well, if we are at the 3 GHz band, where this array will now have a diagonal that is 10 meters, then the Björnson distance is 20 meters. The Fraunhofer array distance divided by 10 is 200 meters. The Fraunhofer array distance is 2 kilometers, and this is 20 kilometers. So we are seeing this Finite-Depth beamforming up to 200 meters. Here are some further illustrations of this. I'm now showing what we are seeing when we're transmitting from an array, and we are transmitting to a point that is perpendicularly away here, infinitely far away. And I'm showing with colors how strong the beamforming gain is going to be. And I can get the maximum beamforming gain in the far field in this case, and we can see that the beam becomes larger and larger. It looks like it's expanding in angle, but it's just because I am using a logarithmic scale here on the axis. So the beam is really starting here, and then it continues and expands. And when we are focusing at near field points, then we have something that is both narrow horizontally in the beam width, and in particular it has a limited depth. So the signal have a focal point, and it starts before it, it ends after it, and behind everything else we are not seeing any amplification. So this is really what I was illustrating in the beginning. We focus a signal at one point and we get like a strong ball of energy around that point, but nowhere else we are seeing any amplification. And how small can this ball of energy be? Well, we showed in a paper a few years ago that the small thing that can happen is really that the radius goes down to lambda divided by 8 when it comes to the 3 dB beam width and depth. So what might we then utilize these kind of features for? Well, one thing we should remember when we are communicating in, for example, line of sight scenarios is that we are transmitting a signal. It has a certain beam width, and then we have a receiver that is having a size that is much smaller than the beam width, which means that it will not be able to see the curvatures, the variations here, so therefore we're only getting 1 degree of freedom. We can only observe one signal transmitted from this point. If we have dual polarized antennas, we can actually separate 2, but for one polarization, there is only 1. But if we take this blue receiver and we move it much closer, so we are in the radiative near field, then what basically happens is that now the beam width is small. And over this receiver aperture, we will actually be able to see the curvatures. And maybe we can now send multiple beams at the same time and be able to separate them at the receiver here. And this way we will have a rank. We can send multiple signals to the user. The rank is greater than 1. And more generally, if we are not trying to transmit multiple signals to the same receiver but to different receivers, what can we do? Well, there is a fundamental limit called the spatial degrees of freedom, and it has been derived in a number of work. Here I present what is beyond massive MIMO, the potential data transmission with large intelligent surfaces is saying. They have a theorem saying that a large antenna array can resolve pi signals. Pi different signals can be separated for each segment of it that has an area of lambda by lambda or lambda square. So what would that mean? Well, suppose we have a plane array with a length L and a height h. Then we are seeing how many segments of size lambda square do we have. Well, L times h divided by lambda square. We multiply that with pi, and that will be the number of different signals that we can resolve, in the sense that we can transmit with, for example, no interference between them. And for a physically large antenna array, which might be, say, 10 meters times 30 meters, and once again we are in the 3 GHz band, you do the math here and you can get approximately 100,000 different signals that this antenna array over the facade can separate. So one from this user and one from a lot of other users around. So we are very far from the limits here. The richness of the channel will actually be determining how many signals we can actually separate. If the users are spread out here, how many objects are there that it's creating sufficient different paths, we have the possibility to separate them. But theoretically, we can separate a huge number here over an antenna array. So finally, then, what are the conclusions? Well, with a physically large antenna array, the users will be in the far field on the individual elements, but they may be in the near field of the antenna array as a whole. So we can separate the signals in terms of the different spherical wavefronts that we are seeing over the antenna array. And this is creating the situation when we have a transmitter here, then up to the Fraunhofer distance, we have all these reactive effects and things that we need to care about for the individual element, but we are typically beyond that one. Then from the Fraunhofer distance up to the Fraunhofer array distance divided by 10, we get what I call near field finite-depth beamforming. And within this range, we have the Björnson distance, where we are losing in array gain compared to the far field, while between that distance up to the Fraunhofer array distance divided by 10, we can get the same array gain from our antenna arrays as if we were using far field models. We just need to make sure that we are compensating for the spherical wavefront variations over the antenna array. And then beyond the Fraunhofer array distance divided by 10, we can essentially treat that as far field. And what we will then utilize these properties for? Well, we can do beamforming with a finite depth in addition to having a small width. And that enables us to multiplex many signals, both to a particular user who's nearby and to many users from large antenna arrays. So when we are talking about the future, we will have to transmit 100 times or 1,000 times more data than in today's networks. Some people are saying, oh, in order to achieve this, we need to go up in frequency so we can get more bandwidth. We need 100 times more bandwidth. Well, maybe an alternative method is to instead let the antenna arrays become 10 by 10 times larger in both dimensions. And in that way, we'll be able to increase the spatial degrees of freedom by 100 times, and in that way, be able to transmit 100 times more data. I think this is a viable alternative that we should explore in 6G and beyond. So with that, I've reached the end here. I would like to send a special thanks to Özlem and Luca, who have been working with me on some of these topics, and also mention some of my funding agencies.